Hello, and welcome back to the last part of Chapter 7. And today we're going to begin with talking about the interaction between two independent variables. So this occurs when the relationship between the dependent variable and one independent variable is different at various values of a second independent variable. And the way you code that is you would do x1 times x2, or the variable that you think has an interaction times the other variable that is also interacting with that. And that will capture the interaction between those two variables. And once you run the statistics for this, the p-value then can tell you whether this is significant or not. That is, if the interaction is significant. And we can go on and make this model as complicated as you want. We could put in some quadratic expressions in here as well. So here we have an example of sales, the mean unit of sales, as a function of selling price and advertising expenditure. So we think there's an interaction between selling price and advertising expenditure. And so we can spend between 50,000 and 100,000, and we can see what that does on our unit sales here. And what this is showing is what if our prices went from $2 to $2.50 to $3, and our advertising expenditure of 50,000 to 100,000, what would that change in the difference in the units sold based on the price as well? And we can see for $2 that if we spend 50,000 up to 100,000, that difference is 347,000 units. For 250, it's the difference between spending that is 282,000. And then if the price was $3, the difference is only 43,000 if we spend the additional 50 to 100,000 in advertising on the number of units sold. So there's an interaction of price here and advertising expenditure. And so that's what this is showing. So if we code our data so that we have another column that has price times advertising, and we run our regression model, we would get output similar to this. So we would see that sales, that's what we're predicting. Here's our intercept. Here's our coefficients for price, advertising expenditure, and price times advertising. So we just plug those in to build our model, and so that's what our model would be. And so as you read along in the book, you note that as the price increases, the more we spend on advertising isn't going to have as great an effect when the price is lower. So that's what this is capturing here. That's what this beta 3 is capturing. So the next thing I want to talk about is some model fitting. In there we'll talk about how do you know which variables to pick, and then what is overfitting. So what you want to do is in your variable selection for your model is you want to pick things that you think are going to be able to help you predict what it is you're trying to model. So sales, maybe price would be a good predictor of that. And so it's an iterative process, set of procedures where you can go through and pick those independent variables. One thing is called backward elimination, forward selection, and stepwise selection. What I like to do personally is if I have a bunch of variables or known variables, I might use something called stepwise selection, where it will generate a model for you, and I would use something like a statistical package like SPSS, and it will actually go out and find the variable that contributes the most in explaining the variance of Y. So it's the variable. It says, okay, this is the variable that should go into the model first. Then it goes out and it does a selection for the second variable that adds the most to the model in terms of explaining variance, and so on. Now you can experiment with this yourself. You could put in different variables and see how it affects the R-squared, the explanation, and see at the model when you plot it how well it maps to what you've got, your data, so that you can then put in values for those different variables and see what it should predict. So if you were to use something like backward elimination, so that begins with a regression model that includes all your independent variables, and backward elimination considers the removal of an independent variable according to some criterion. And then the stopping condition is when all the independent variables in the model are significant at some level of significance that you've set. Forward selection begins with none of the variables in your regression model, and then it considers the addition of an independent variable according to some criterion that you set. The stopping condition is when no independent variable that's not in the model that meet the criterion for adding to the regression model, so that you can't add anything else. They don't meet the criterion. Stepwise, then, you don't have any of the independent variables in, and you look for a criterion for allowing independent variables to enter the model, usually significance. And then the most significant independent variable is added to the empty model. And if that level of significance is satisfied, it meets the threshold, you add some more. And then that continues until it doesn't, adding more variables doesn't meet that level of significance for being in the model. Now note these two steps here. So it enters a variable in. If it's significant, it puts it in. Then it looks at the models, the independent variables that are in the current model, and the least significant one is removed. And so what you're not, if one is more significant that gets put into the model, then that least significant one gets taken out. And it still goes through the process of seeing if it should be in at the end or not. But if it doesn't meet the criteria of adding extra, then it doesn't go into the finished model. There's also something called best subsets. Here you start with a simple linear regression for each of the independent variables, and then multiple regression with all the combination of two independent variables. Once that you generate a model for every possible subset of the independent variables, then the entire collection of all those models are compared and evaluated. So again, the one that explains the most and is the best fit to your data then would be chosen. Now there's something called overfitting, and that happens when you have a very complex model and you try and manipulate everything so you're explaining a whole bunch of variance for the data you have. And what overfitting is that you've created a model that predicts the data that you have so well, but when you try and see how well it predicts other data that you know the output, what the output should be, it does a terrible job. Okay. So if you overfit, it will perform better on the sample data, but it will do terrible on outside data. And really, the way you do that or check for that is you might have a data set and you'll say, okay, I want to randomly select 10% of the population or the sample size to be a holdout that the model wasn't used, the data wasn't used to predict that model, so that holdout sample data will then be used to see how well the model predicts data that it was never used to create it with. I hope I'm explaining that correctly. So let me try that again. So let's say you had a sample of 100. And instead of doing a regression on that sample of 100, you might take out 10% or 10 observations. You'll then create a model of your data with only 90 in your sample data. So it tries to get the betas and everything else correct, whether you've got interaction or quadratic, whatever. And then once you've decided that, then you take that data that it was never used to build the original model with and see how well it predicts that. If it does a good job, then you've got a good model. If you've overfit, then it won't do as good a job, an R² value, as your original data, those 90 sample sizes would. So some things you can use to avoid overfitting. Use only independent variables that you expect to have real and meaningful relationships. Use complex models like the quadratic model, piecewise linear regression models, only when you think there's a reasonable expectation that that complexity provides you some more accuracy in your model. Don't let the software dictate what you're going to do with your model. Right? So you want to use those iterative modeling procedures like stepwise and best subset procedures to help you guide in what you want to eventually choose as the model that's going to fit your data. And if this is the first time you've ever been exposed to it, it's just a matter of practicing and building your model, and then seeing whether that holdout sample works or not, and then learning from, okay, I've overfit this because I've made the model too complex. I put in too many extra variables that, yes, explain, once the model is built, explain a lot from the original data, but that holdout data doesn't work with all that complexity I put in. So what I've been explaining is, to do some cross-validation, and what I explained was the holdout method. There is also a k-fold cross-validation and a leave one out cross-validation. When you use that holdout method, you'll have the training set, that's your original data, and then your validation set to see how well the model predicts. With k-fold cross-validation, you'll come up with a sample data and randomly divide that in k equal sized, mutually exclusive subsets. And each one of those subsets is called a fold. And then you'll train and test with that. With the leave one out cross-validation, you might have a sample of, say, 100 observation, and then so n-1 observations, and evaluate the model on the single observation that was omitted. So if you had, say, 1,000 and you're doing every 30, then you take one out of that 30, see how well you did it, take the next set, so on. And then we have some things to talk about in terms of big data and regression, and we've said a lot about that previously, given that if you have a huge amount of data, almost everything becomes significant. And so the way that impacts your model, then there will be little difference in the beta values generated by different random samples. So each beta 1 would be very similar from the different random samples, beta 2, and so on. Here we have some data that the book used for big data and regression, and it's based on 3,000 observations in a training set. So the R² is 0.36. It only explains 30%, 36% of your predicted value from the independent variables. So we've got an intercept, annual sales or annual income, household size, and years of post-high school education. And what we're trying to predict is annual credit card charges. Right, so we can see that we have large data sets of 50 observations coming out of that, and we can see what we've predicted. So here we have 150, 100 observations. These are just different data sets, and we can see what the betas are for each one of those values and the p-values. And what happens if we add the number of hours per week spent watching TV? You know, we can see from a large data set, the p-value is significant and it doesn't cross zero. But does that make any sense? So the more number of hours you watch TV, the higher your credit card expenditures or charges are going to be. So some guidelines then. So when you're dealing with large samples, it might be hard to find the best model. You have to look at those betas and then do the interpretations like we've been explaining through this chapter. Hold everything else constant and say, okay, if I have a value of 1 increase for this independent variable, then does this really make sense that it increases my y value, what I'm trying to predict, by this amount? So you might develop different models. And so here what we're showing is the comparison of 2 models that we're using that large credit validation set, and then see how well they predict on, say, a validation set of 2,000 observations. And you can see that sum of squared error here, not real, much in the terms of difference, but maybe enough difference that might help you predict, not predict, but use or select one model over another. The last part deals with prediction and regression. And something else you probably need to be aware of is there's 2 types of interval estimates that you can have with regression equations. We have a confidence interval, and it's an interval estimate of the mean y value given values of the independent variable. So y hat plus or minus the t statistic divided by t times your standard deviation of your estimated y. There's a prediction interval then of the individual y values given the values of the independent variable. So that equation looks like the following. So here we have, if we go back to our Butler trucking example, we have the predicted values, that's our y, and 95% confidence intervals and prediction intervals for 10 new Butler trucking routes. So the example here is for all 105-mile routes with 3 deliveries. A 95% confidence interval on the mean travel time is 9.25 plus or minus 0.193. And so there's a 95% confidence that the true population mean travel time for this 105 miles with 3 deliveries is between 9.06 and 9.44 hours. And that ends this chapter.